Friends, welcome back again to another BrainFlex video. In this one, we are going to answer questions from 2022, tutorial sheet 1. So we are going to answer questions from question 6 to question 11. Okay, let's begin. So question 1, our first question will be question 6, which is how many significant figures are in the following numbers? So we are given the number 78.9 plus or minus 0.2. Okay, so we know that this number has uncertainty, so this last part, it's uncertainty. To be specific, it's called absolute uncertainty. Then we have this part, which is called the central value. So if you are told to state the number of significant figures of a number of this kind, you need to ignore the uncertainty part. So this part, ignore it. And just focus on the central value. Okay, now focusing on the central value, we can count the number of significant figures as 1, 2, 3. So we have 3 significant figures. Remember, non-zero digits are considered as significant. So we have 3 significant figures. Okay, so that's it for A. Now let's jump to B. So B we are given 3.788 times 10 to the power 9. So this number, it's in standard form. Yeah. So if you're given a number in standard form, you need to focus only on the coefficient. This part. So you focus on the coefficient. So how many significant figures are in our coefficient? We have 1, 2, 3, 4. So we can say we have 4 significant figures. You ignore the exponent this side. Okay, so just focus on the coefficient. Don't forget on this one. Okay, we have another number in standard form, which is 2.26 times 10 to the power negative 6. So in this one, 2, we need to focus on the coefficient, and the coefficient has the following number of significant figures: 1, 2, 3. Remember, these integers are, these digits are non-zero digits, so they are considered as significant figures. Okay, so we have 3 significant figures. Okay, I've noticed I've been making a mistake between integer and digit. Don't forget, these two, they are not one and the same. So each time I say integer, please just know I'm talking about digit time, but they are not one and the same. I think in future I won't make that kind of a mistake. Yeah. Okay, so let's handle D. So D, we are given 0.0053. Remember, we have a rule that states leading zeros are not significant. So these ones, the leading zeros, are not significant, regardless of us having a point there. Provided they are leading zeros, they are not significant. So we have 2 significant figures in this one. Now, what about if you had a number of this kind, 1.0053? How many significant figures are in this particular number? In this one, because the zeros are between non-zero digits, we count them as as significant. So we're going to say we have 1, 2, 3, 4, 5 significant figures in this one. Okay, for the sake of learning, let's have another example. Let's say we have a number of this kind. Let's say we have 74.200. How many number of significant figures are in this number? Remember, we have another rule that states trailing zeros are are significant. So these ones, they must be counted as significant because they are trailing what? Zeros. So trailing zeros in a number with a decimal point, by the way. So if a number has a decimal point and you have trailing zeros, consider those trailing zeros as what? Significant. So in this one, we have 1, 2, 3, 4, 5. We have 5 significant figures. Reason why? It's because we have trailing zeros in a number with a decimal point. Okay, I think this is enough. By the way, if you're not familiar with loose significant figures, loose, you can check out our video that we've created specifically for that topic. It's titled Significant Figures, Full Explanation. Yeah, I think that's how I titled it. Significant Figures, Full Explanation. You can check it out. Okay, let's jump to question 7. So question 7 says, the radius of a solid sphere is measured to be that amount, and the mass is that amount in kg. Determine the density of the sphere in these particular units. So we are saying we need to determine them in kilograms per meter cubed. Take note of that. And the uncertainty in the density. Wow. So we need to consider uncertainty too. Okay. So let's begin by calculating the density. We can get rid of these things too. So to calculate the density, we know that density is equals to mass over volume. Are we given volume in this question? The answer is no. We are given the radius. So we are told that the radius is equals to 6.50 plus or minus 0.20 centimeters. We are given this one as the radius. Okay, let's find the density. So we know that in a number of this kind, this part, we call it the central value, while this last part, we call it the uncertainty part or the absolute uncertainty. So to calculate the density, like the first part of our question, which is determine the density, we are going to take our central value. So let's get our central value. So we are saying radius is equals to 6.50 centimeters. Let's convert it into meters since our density must have this kind of unit, which is meter cubed. So let's convert it into meters. So we're saying 6.50 centimeters can be converted using this conversion factor. 100 centimeters is equal to 1 meter. So that the centimeter and centimeter will cancel, we are going to have 6.50 divided by 100. Okay, let's punch that into our calculator. Let's punch it. Divided by 100, you are going to get a value of 0.065 meters. Okay, so we have this one as our radius in meters. Now, let's find the volume. We know that the volume of a sphere is given by 4/3 pi r cubed. And we know that r is equals to 0.065 meters, by the way, cubed. Let's punch that into our calculator. We are saying 4/3 multiplied by pi multiplied by 0.065 to the power 3. We are getting a value of 1.15035 times 10 to the power negative 3. Units, it's meter cubed or cubed meter. Okay, so that's our volume. Now let's calculate the uncertainty in volume. So to calculate the uncertainty in volume, we can now calculate our uncertainty in volume. Okay, before we do uncertainty in volume, let's first find the density. Remember the question says density, and what we have here is the volume. Let's finish up this part. So we are saying density will be equal to the mass we are given, this amount. So we are going to get the central value, which is 1.85 divided by that amount. So we are saying kg there. At the bottom we have 1.15035 times 10 to the power negative 3 meter cube. Okay, so punch that into your calculator. So we are saying 1.85 divided by 1.5035 exponent negative 3. Okay, I'm getting a value of, okay, you're going to get a value of 1608.21107 kg per meter cubed. Okay, let me write that at the bottom. You're saying kg per meter cubed as your density. So we are done with the first part of the question, which is determine the density of the sphere in that particular unit. Now let's do the last part, which is uncertainty in density. Okay, let's jump to the last part. So we need this value. So I'll write it there. We need this value. Let me actually round it off to 1608. Okay, I'll just write it in full. And we'll do the rounding off at the end. Kg per meter cubed. Now let's get rid of everything. Okay, let's now find the uncertainty. So to find the uncertainty, you need to know the following. If you have a formula that has a power in it, we say power times percentage uncertainty. Now what I mean by this is that if you have a power like this one, to find the uncertainty in volume, you are going to focus on the, you're going to ignore the constant. So in this particular formula, this part is considered as a constant. It's dimensionless. So this part is considered as a constant. So you ignore the constant and focus on the variables that have dimensions. So r has a dimension, it's a length. Yeah. So ignore the constant. So in this one, we have r to the power 3 as volume. Yeah. So volume is proportional to r to the power 3. Okay. Now, having said that, let's do it. Oh, one more thing. So this is one of the formulas you need to know. If it has a power, you say power times percentage uncertainty. But if you're dealing with a formula that has to do with multiplication, for example, if you're dealing with a formula like for area times b, in this one we have multiplication as the mathematical operation in it. We say we add. So if you're dealing with multiplication, you add. We are saying add percentage uncertainty. Okay, having said that, let's do it. So you add percentage uncertainty. There's actually an extra rule that you need to know, but you can check out my video titled Uncertainty in Measurements. Okay, now that we've made mention of this, let's now do the question. So to find the uncertainty in volume, we know that volume is proportional to r to the power 3 for a sphere. So we are going to say 3 times percentage uncertainty. Now we know that percentage uncertainty, when you say percentage uncertainty, is given by absolute uncertainty divided by central value multiplied by 100%. So let's punch that here. So we're going to say absolute uncertainty for volume, for R. Remember dealing with volume at this point. So R, we're going to get that one, the absolute uncertainty, which is 0.20. The central value is 6.50 times 100%. Let's put these things in brackets. Okay, so the volume part will give us 0.2 divided by 6.5 times 100 times 3. And you're going to get a value of 9.2308%, by the way. Okay, now let's do for mass. Yeah, let's do for mass. So for mass, we need to find the uncertainty of mass. This is the uncertainty for volume, by the way. This one is for volume. Let's do for mass. So for mass, we know that mass we are given. No need of doing any calculations. So we just need to plug in the values into this formula. Okay, let's do it. So percentage uncertainty for mass will be 0.02 divided by 1.85 times 100%. And that will give you a value of 0.02 divided by 1.85 times 100%. You're going to get a value of 1.08108% as that for mass. Okay, now to find the density, the uncertainty for density, we need to look at the formula. So density is given by mass over volume. And remember what I said, multiplication, you do what? You add the percentage uncertainty. So for division, for multiplication, you add as well as for division. So if you're dealing with division or multiplication, you add the percentage uncertainties. So I'm going to add the two because in our formula for density, there is division between mass and volume. So I'll add the two percentage uncertainties to find the percentage uncertainty for density. So we are saying this one will be added by that one. So let's say plus 9.2308. And the value will be 10.31185031%. Okay, so this one is for density. And we are done. So you can write now your solution as, you can write it as, you can say our answer is 1608.2 21 plus or minus 10.31%. In what? In kg per meter cubed. So that's how you handle a question of this kind. But we are not yet done because some lecturers prefer writing the uncertainty part, this part, as absolute uncertainty. So you might be taught to write it as a decimal number. So to write it as a decimal number or absolute uncertainty, you need to convert it back. So we know that percentage uncertainty is equals to absolute uncertainty divided by the central value multiplied by 100. Take note of that. So if you are given percentage uncertainty as 10.31%, the absolute value is what we're interested in. The central value are given as 1608.21 times 100%. To find the absolute uncertainty, we can say 10% times 1608.21 divided by 100. And the value will be 165.8 0.84. Okay, we can now write our answer. We can write now our answer as follows. Okay, wait a second. So we have this value. Okay, yeah, it's correct. So we can write it as 1608.21 plus or minus 165.84 kg per cubic meter. Yeah. So that's how you can write your solution. Okay, so that's it for this part. Let's jump to question 8. So question 8, we are told to compute the value of this summation. Wow. The value for this summation. So we are told to compute the value of that. Okay, so we are told to compute the value of this particular summation. On top we have 4, and there we have 4i. And we are told that xi is equals to 2i plus 1. Okay, so if you are given something that looks like this, what you must know is that this bottom part is known as the index. The top part, actually, let's call it the lower limit. So this one is just the lower limit. And the top part is the upper limit, the ending point. And how to compute this one, it's like this. If you have a summation, let's say on top we have a 3, on the bottom we have I is equals to 1, and this side we have, let's say, I. So if you're told to compute something that looks like this, this means that you substitute 1 into this particular expression that we have this side. By the way, this part is called the expression or the function. So you replace I, or the value of I, into this particular expression in ascending order until you reach the value of what? 3. Okay, so this means we need to say 1, we replace it there, plus. From there, I'm going to jump to 2. We replace it there to be plus 2. From there, I'm going to jump to 3, plus 3. Now that we've reached the upper limit, we end there. And we're going to say 1 plus 3, that's a 5, plus 1, that's a 6. So that's how you compute something that looks like this. Okay, so if we add something with a power on top, let's say we have a power 2 there, we could have said 1, I there, then we have 1 there. We could have said 1 there, we substitute it into this expression. I'm going to have 1 to the power 2. If we substitute the next value, which is 2, it will be 2 to the power 2, then 3 to the power 2. Then from there, you can say 1 plus 4 plus 9. Okay, 9 plus 1, that's a 10, plus a 4, that's a 14. So that would be your solution. Yeah, your solution. Okay, now let's come back to our question. So we are given this question, and we are told that this x with a base of I is equals to 2i plus 1. So we can write this particular expression as 4 summation of I is equals to 1 of 2. Let's substitute what is this with that, with this. So we can say we have that. Then from there, just a matter of substituting I there into the expression. So we're going to have 1 plus 1 plus, open, 1, then you're going to have a 2 plus 1. Then from there, we're going to say plus, then we're going to have a 2, open, a 3 there, plus 1, plus, open, 2, a 4 there, plus 1. Remember, the numbers are doing what? Are ascending until we reach the what? The upper limit. Okay, so now that we've reached the upper limit, we end there. Just a matter of now punching that into your calculator. So 2 times 1 is a 2, plus 1 is a 3, plus 2 times 2, that's a 4, plus 1 is a 5, and 2 times that one is a 6, plus 1 it's a 7. This one it's a 8, plus 1 is a 9. Then from there you can say you add. So we are saying 3 plus 5, that's a 8, plus a 7, plus a 9. And you're going to get a value of 24 as your solution for this particular question. Yeah. Okay, so this one is very easy. Let's go to question 9. Okay, question 9 says, the square of speed of an object undergoing uniform acceleration a is some function of a with displacement s according to the expression given. So we're given that expression, which is v squared. Okay, let's write it there. V squared is equals to k a to the power m s to the power n. Then we're told that k is a dimensionless constant. And the question says, show by dimension analysis that the expression is satisfied only if n is equals to 1 and m is equals to 1. Okay, so to do that, by the way, if you see a question of this kind, it falls under checking or verification of an equation. It falls under verifying or checking an equation whether it's dimensionally correct. Under that part of dimension analysis. So to check whether this is correct, what we can do, we can begin by writing each dimension in the formula, in its dimensional formula. Okay, let me repeat that. So we're given this formula, so we're going to write each dimension in its dimensional formula. So we have velocity. Velocity, we know it has a unit of meters per second, and its dimensional formula will be L dot t, representing seconds, to the power negative 1. And k is a dimensionless constant. We know that dimensionless constants are equal to 1. So k is equals to 1. Then m will be equal to meters second squared, which means it's L dot t to the power negative 2. Then s represents displacement, which is m, so it can be written as L. Okay, so when you reach this stage, you can be given a mark. Now your next step will be plugging this dimensional formulas into your given equation. Remember, we are trying to check whether the equation is dimensionally correct. So let's plug them into our equation. So when you plug them into our equation, velocity, okay, so velocity, let me write that part. We are saying velocity, this part, will be squared, will be equal to k, it's 1, acceleration is that value, so we're going to say L and we need to power this to m. Then from there we need to multiply it by displacement, which is L, and we need to power it to n. Okay, we won't be needing these things anymore. So we've plugged them into our equation. Now let's simplify it. So the 2 will be power that one, so L2 will be L to the power 2, and t will be to the power negative 2, and that will be equal to L will have a power of m, then t will have a power of negative 2m, and we're going to have L to the power n. Now we know that this one and that one can combine, and we're going to get a L to the power m plus n dot t to the power negative 2m. This side we have L to the power 2 and t to the power negative 2. Okay, let's create some space. So now we can now develop some equations by saying L, when you take the L part, this part corresponds to that part. So we can say L, that one is equal to L to the power m plus n. And T, when you take the T part, it's this one, the T to the power -2 corresponds to T to the power -2m. Okay, let's create some space now. So on this part, we know that the bases can cancel. We are going to have -2 is equals to -2m, which means m is equals to 1. Wow. This side, we know that the bases can cancel and we can have the powers as m plus n. And we know that n is 1, so it would be 2 is equals to 1 plus n. So n will be equal to 2 minus 1, which is equal to 1. Okay. We are done. We have shown that this particular equation is satisfied when n is equals to 1 and m is equals to 1. So when you look at it, we can see that n is equals to 1 and m is equals to 1. So we have shown by dimension analysis that the expression is satisfied only if n is equals to 1 and m is equals to 1. So that's how we go about a question of this kind. Okay, let's do question 10. So question 10 says, the period represented as capital letter T of a simple pendulum is measured in time units and is given by T pi, then the square root of length over gravity. We are given this one. Let's see, what's the question in this one? That one over gravity. I can't see any question. Okay, we have the question there now. Where L is the length of the pendulum, G is the gravity, is the acceleration due to gravity in units of length divided by the square of time, or K. So we are given that gravity as units, length divided by the square of time. Okay, so it can be written as that. Show that the equation is dimensionally consistent. Wow. So in other words, we are just showing that the equation is dimensionally correct. Okay, so it's the same as the question we did on question. It's the same as question 9. Yeah. So first step, you need to write each given dimension in its dimensional formula. So we are given T. T can be written as T, by the way, we are given that T, it's what? We given T. T, we are told that it's the period of a pendulum. So period of a pendulum, we know that it has units, seconds. So it will be T. Remember, if you know the units, it's easy to write the particular dimension, its dimensional formula. So we know that the unit is second. So we can just say its dimensional formula is T. Okay, let's write the dimensional formula for L. L is length, so length is measured in meters. So we can say it's L as the dimensional formula. We have what else? G, we've written it. And 2 and pi, these ones are constants. So 2 pi is equals to 1. It has a dimension of 1. So no need of writing it down. Okay, so now it's just a matter of plugging these ones into our formula. So we are saying T will be equal to the root of L it's that, over G. G, we are given T, it's L, that one, dot T to the power -2. Okay, let's evaluate this one. Let's create some space this side. So now we can write the root as power, we can write it as power negative, power 1 over 2, and this one can be written as power 1 over 2. So now we can have t is equals to L to the power 1 over 2 dot L, so it would be L to the power negative, since it was at the bottom, it would be negative 1 over 2 dot T to the power negative, the negative here will turn into a positive, so it will be plus 2, multiplied by that, so it will be times 1 over 2, which is just a 1, so we can just say 1. So now from there we can have the following. This part and that part will give us, you add the power since the bases are the same, so we can say half minus half. So half minus half will give us a 0. Wow. Then the t this side, we know it's to the power 1, so no need of putting a 1 there. Anything to the power 0, we know it's 1, so this part will give us a 1, so we can write a 1 there. So from there now we can see that t is equals to t. So from here now it's just a matter of saying hence, we can say hence shown. We have shown that this particular equation is dimensionally consistent, because this part and that part, they are equal. Okay, so that's it for question 10. It's very, very easy if you know what you're doing. By the way, when you're writing your dimensional formula, always write it this way. Type the letters inside and always put this type of brackets, the square brackets, to show that it's a dimensional formula. Yeah. If you follow those steps, you get the full marks for questions of this kind. Okay, let's do the last part. So the last part says we are told to convert these measurements into units, into given units. Then we are told that give answers in standard scientific notation. Okay, so our first one is 204.0 kg. To do any kind of conversions of this kind, you need to know what we call metric system. Yeah, so under metric system, we have this mnemonic, which is the great mighty King Henry died by drinking chocolate milk Monday night picture. Yeah, so this one it's Tera, that one it's Giga, that one it's Mega, this one it's Kilo, that one it's Hector, this one it's Deck, this one is the basic unit, the base, this one it's Des, that one is Cent, this one Milli, that one Micro, then we have Nano and Pico, and finally we have Pico. Okay, so you can write that one down in full words. Yeah, so our base as 1, then followed by 10 to the power 1, followed by 10 to the power 2, then from there it's 10 to the power 3, then 3, when you add 3 plus 3 to the power, it will be 6, so there it will be 6, then 6 plus 3, it will be 10 to the power 9, then 10 to the power 12. This side we are going to have 10 to the power negative 1, then from there it's 10 to the power negative 2, then 10 to the power negative 3, then 10 to the power negative 6, then 10 to the power negative 9, then 10 to to the power negative 12. Okay, now that we've established the metric system, it will be easy now to work out these questions. So here we are told to convert kilograms into milli. So we are going to convert from kilograms, where's kilograms? Here, from kilograms to the basic unit. So we're going to convert it to basic unit, then from basic unit to milligram. Okay, let's do it. So kilograms to basic unit, we're going to use this conventional factor. We know that kilogram, it's what? It's 10 to the power 3. So we're going to give it our basic unit, which is gram in this case, divided by, then at the bottom we're going to say this is equal to 1 kilogram, since we're dealing with a kilogram, then multiplied by, we need now to convert the base unit to milli. So to convert it into milli, we know that we're going to put grams at the bottom so that they cancel, and we know that per every 10 to the power milli as to the power negative 3, we have 1 milligram. Okay, the kilogram will cancel too. We're going to remain with milli as the units. Now it's just a matter of punching those ones into your calculator, which will give you a value of 204,000. Yeah, as your value. Now, if you end at this point, you'll be given a half mark. To get a full mark, you need to write it in standard form. So to write it in standard form, it will be 2.04. So the point has moved from this point to 1, 2, 3, 4, 5. So it has moved 5 steps. So it will be 2 to the power 5 milligrams. Okay, so if you write it this way, you're going to get the full marks. Okay, now let's do B. So B, we are given 503. So we're given 503.8 centimeter cubed. Okay, this one has a cubed in it. So to convert a unit from centimeter to liters, we need to know that a liter is equal to 1 decimeter. 1 decimeter cubed. It's what we mean by a liter. Yeah. So we need to convert it to decimeters. So to do that, we're going to say this particular unit has to be first converted from centimeters. Where centimeters? There. So from centimeters, we're going to convert it to the base unit. Then from the base unit, we're going to convert it to decimeters, which is this point. Okay, let's do it. So basic unit first. So to convert it to the base unit, it will be how many? It will be 10. Since it's centimeters, it will be 10 to the power negative 2 meters. It's equal to 1 centimeter. Yeah, it's equal to 1 centimeter. So this part and that part will cancel. The answer is no. We have a power 3 there. So to get a power 3 there, we need to power everything to 3. So I'm going to put a 3 there. Yeah. So this part now can cancel that part. So I'm going to remain with meters. So now we need now to convert meters into decimeter. So to do that, we're going to say every 10 to the power negative 1 meters, we have, remember, decimeter is 10 to the power negative 1. So we have 1 decimeter. So that part and that part will cancel. The answer is no. We need to put a power 3 for them to cancel. So that part and that part can cancel. And we're going to remain with decimeter cubed as our answer. So let's do it. So we are saying we have 5, 0, that one, 8. The units have cancelled. Let's power 10 to the power negative 3. So that power times that one will be negative 6. So it will be 10 to the power negative 6 over 1 times 1 to the power 3. It's a 1. So we're going to get a 1 decimeter over 10. The 3 times negative 1 will give us a negative 3 at the bottom. And these two can cancel. You're going to get a 10 to the power negative 3. Yeah. So we can write it as 10 to the power negative 3 decimeter cubed over 1. Okay, let's punch that now into our calculator. So we are saying 10 to the power negative 3 multiplied by 503.8. And you're going to get a value of 0.50380 as your decimeter cubed. In other words, we are saying as liters. Okay, let's create some space. Now let's write it in standard form. So in standard form it will be 5.038 times 10 to the power. Now this will be to the power. For the point to move to that point, it has made one step to the left, so it's negative 1, so it will be negative 1. What are the units? We are saying liters. So that's how you handle a question of this kind. Okay, so this one must be your solution. Let's now handle question C. So question C, we're given this number of meters and we're told to convert them into decimeters. Okay, I'll skip this one. I want you to try it out. Yeah, since we did similar stuffs to this one. Yeah, you do it, then send me the solutions. Yeah, you can inbox me the solutions. So I'll skip this one. Let's go to question D. So question D says we have that number of liters and we're told to convert them into kiloliters. This one too, I'll skip it. It's straightforward. Let's do the last question, which is 60 kilometers per hour into meters per second. Wow. We know first that in 60 seconds, we have 1 minute. And in 1 hour, we have 60 minutes. Yeah, take note of that. So now let's do the conversion. We're given 60 kilometers per hour. So we can write it this way. This one can be converted as follows. So we need to convert it into meters per second. Let's begin by converting the distance part. So meters into kilometers, we know that per every 1 kilometer, we have 1,000 meters. And to convert time, we can say per every hour, we have 60 minutes. And per every minute, we have 60 seconds. That part and that part will cancel. This one and that one will cancel. Kilometer and kilometer will cancel. We are remaining with now meters and seconds. So when writing your conversion factors, write them in a strategic way whereby the units are cancelling. So if you have seen, I wrote deliberately 1 minute on top so that it can cancel with the 60 minutes on the bottom in this conversion factor at this stage. Yeah. So now from there, just a matter of you now punching it into your calculator. We know that we are getting meters and seconds, so over seconds this side. So now just a matter of you punching it into your calculator. So you're saying 6 has to be multiplied by 1,000, then divided by 60, and again divided by 60. So when you do that, you need to get okay, let me do it again. We are saying 60 has to be multiplied by 1,000. You get that value. Then we need to divide it by 60. So we're saying divided by 60. Then once you get your value, you need to divide it again by 60. So your answer will be 1.6 6, 6 with a bar on top. So it goes on and on and on and on and on. So this one will be your solution for E. So that's how you answer questions that involve conventional factors. Please don't forget to memorize this mnemonic, which is the great mighty King Henry died by drinking chocolate milk Monday night picture. Yeah, you can memorize it. It will be very easy when dealing with conventional factors. Oh, by the way, this answer is not complete. We need to write it in standard form. I forgot. We need to write it in scientific form. So to write it in scientific form, we can say 0. We can just shift this one to this step. 0.167 times 10 to the power, let's give it to the power, since it moved one step, it will be to the power 1 meters per second. Yeah, you can write it that way. Okay, in future, I will consider significant figures when answering questions of this kind. Yeah, but meantime, you can just do what I've done. But in my future videos, I will consider significant figures when answering question of this kind. Okay guys, that's it for this video. If you enjoyed the lesson, you can consider registering to have access to more of our videos.